close your eyes and let yourself drift far beyond the familiar blue sky, beyond the clouds and the atmosphere, into the gentle darkness of space. Tonight, we're going on a journey together, a slow, peaceful voyage through our solar system, where we'll discover the quiet wonders of worlds both near and far. Let's begin our story where all stories of planets must begin, with the Sun. Not a planet itself, but the warm, golden heart around which our planetary family gathers. Imagine it now, a sphere of light so vast that over 1 million Earths could nestle inside it. Yet despite this enormousness, the Sun is gentle in its own way, quietly converting hydrogen into helium, creating the soft warmth that reaches across millions of miles to touch your face on a spring morning. It has been doing this same patient work for about 4.6 billion years, and it will continue for billions more, a cosmic lighthouse guiding its planetary children in their endless dance. And dancing closest to this luminous parent is Mercury, the smallest of our true planets. Picture Mercury as a swift messenger, racing around the Sun in just 88 Earth days. This little world, barely larger than our moon, moves so quickly through space that ancient astronomers named it after the Roman god with winged sandals. But here's something wonderfully strange. While Mercury hurries through its year in 3 of our months, a single day on Mercury, from one sunrise to the next, lasts 176 Earth days. Time itself moves differently there, stretched and dreamlike, as if the planet is reminding us that speed and slowness can exist together in the same small world. If you could stand on Mercury's surface, though you'd want to choose your spot carefully, you'd witness one of the most extreme environments imaginable, yet there's something almost poetic about its contrasts. During the long day, temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead into silvery puddles. But at night, with no atmosphere to hold the warmth like a blanket, the temperature plummets to minus 290 degrees Fahrenheit. It's a world of absolutes, of fire and ice taking turns across the same ancient, cratered ground. Now let your mind drift further outward, to our second planet, Venus. Beautiful, brilliant Venus, the evening star that has captured human imagination since we first looked up at the twilight sky. Venus shines so brightly not because it's the closest planet to us, though it does come nearer than any other, but because it's wrapped entirely in thick, reflective clouds. These clouds create an almost pearl-like glow, making Venus the brightest natural object in our night sky after the moon. For thousands of years, people made wishes on this star, never knowing they were whispering their hopes to an entire world shrouded in mystery. Venus keeps a secret beneath those luminous clouds, a secret that makes it one of the most intriguing worlds in our celestial neighborhood. While it appears serene and beautiful from Earth, Venus spins in the opposite direction of most planets in our solar system. If you could stand on its surface and watch the sun rise, though the thick clouds would make this impossible, you would see it rise in the west and set in the east, a backwards sunrise in a backwards world. This gentle rebellion against the cosmic norm gives Venus a quiet uniqueness, like a dancer moving counter to the rhythm yet still perfectly in time with something we cannot hear. And Venus takes its time with this backwards dance. A single day on Venus, one complete rotation, lasts 243 Earth days, which means a day on Venus is actually longer than its year, which takes only 225 Earth days. Imagine that. You could celebrate your birthday before you've even seen a single sunset. Time becomes something fluid and strange, bending in ways that challenge everything we know from our experience here on Earth. Perhaps this is why Venus feels so dreamlike, so perfect for this moment as you settle deeper into rest. Beneath those reflective clouds lies an atmosphere so thick, so heavy, that the pressure on Venus's surface is 90 times greater than the pressure at sea level on Earth. That's the same pressure you'd experience if you dove nearly a mile deep into our oceans. The atmosphere presses down like a heavy, warm blanket, so dense that if you could somehow survive there, you could almost swim through the air itself. And within this dense atmosphere, the temperature reaches a scorching 900 degrees Fahrenheit, hot enough to melt lead, hot enough that the surface glows a faint orange in the darkness, like embers in a cosmic fireplace. Now let us drift homeward, to the third planet, our own precious Earth. After the extremes of Mercury and Venus, Earth appears like a sanctuary, a refuge of perfect balance. Here is a world where water exists in all three forms at once: solid ice at the poles, liquid oceans covering 70% of the surface, and vapor drifting as clouds in our atmosphere. This trinity of water is rare, perhaps even unique in our immediate cosmic neighborhood, and it makes Earth a living jewel, blue and white and swirled with weather systems that shift and breathe like the planet itself is alive. Our Earth spins at just the right speed, completing one rotation every 24 hours, giving us the familiar rhythm of day and night that has governed life for billions of years. And as it spins, it also journeys around the Sun, taking 365 days to complete one orbit, tracing an invisible circle through the darkness of space. But Earth doesn't travel this path alone, and this is where our story finds one of its most gentle truths. Accompanying Earth on its journey is the Moon, our faithful companion, our silver guardian in the night. The Moon orbits our planet at an average distance of about 238,855 miles, close enough that we can see its face clearly on cloudless nights, far enough that it takes light just over a second to travel between us. But here's something that makes the Moon truly special: it's slowly, almost imperceptibly, drifting away from us. Each year, the Moon moves about 1.5 inches further from Earth, a gradual farewell measured in increments so small they seem like whispers. Yet even as it drifts, it continues its ancient duty, pulling at our oceans to create the tides, a rhythm that has persisted for over 4 billion years, reliable as a heartbeat, constant as breath. Let your thoughts drift now beyond Earth, past the Moon's gentle glow, to the fourth planet from the Sun, Mars, the Red Wanderer. Mars glows with a rusty, orange-red hue that ancient civilizations associated with fire and war, but up close, this world reveals itself to be far more serene than its color suggests. The red comes from iron oxide, common rust, covering much of the Martian surface, as if the entire planet is slowly, peacefully oxidizing under the touch of time. It's a world painted in shades of sunset, perpetually caught in that golden hour we love so dearly here on Earth. Mars is a smaller world than ours, roughly half the diameter of Earth, with about 1/10 of our planet's mass. If you could somehow transport yourself there, you'd feel immediately lighter. Your weight would be just 38% of what it is on Earth. Imagine that lightness, that ease of movement, as if gravity itself has decided to give you a gentle reprieve. Each step would carry you a little further, each jump would lift you a little higher, as if Mars is inviting you to dance across its ancient, dusty plains. And what plains they are! Mars holds the title for the largest volcano in our entire solar system, Olympus Mons, a shield volcano so vast it challenges comprehension. Rising about 13.6 miles above the Martian surface, Olympus Mons is nearly 3 times the height of Mount Everest. But its true majesty lies in its breadth, approximately 370 miles across, roughly the size of the entire state of Arizona. If you stood at its center, you wouldn't even perceive you were on a mountain. The slope is so gradual, so gentle, that the horizon would hide the truth from you. It's a giant that lies down in humility, a mountain that whispers rather than shouts. Mars also harbors the deepest, longest canyon system yet discovered in our solar system. Valles Marineris stretches about 2,500 miles along the Martian equator, so long it would span the entire width of the United States, from coast to coast. In some places, this magnificent scar in the planet's surface plunges 4 miles deep, with walls that drop away into shadow and mystery. Scientists believe this canyon system wasn't carved by water like our Grand Canyon, but formed billions of years ago as the planet's crust stretched and cracked, an ancient wound that has never healed, preserving a moment of planetary transformation frozen in stone. But perhaps the most touching thing about Mars is its seasons. Like Earth, Mars has an axial tilt, about 25 degrees compared to our 23.5, which means it experiences spring, summer, autumn, and winter, just as we do. However, because Mars takes 687 Earth days to orbit the Sun, each Martian season lasts about twice as long as ours. Imagine a spring that lingers for months upon months, a summer that seems to stretch toward infinity, an autumn that gives you all the time in the world to watch the leaves fall, except, of course, there are no leaves on Mars, only dust storms that can engulf the entire planet, transforming it into a hazy, amber dreamscape where the sun becomes a pale ghost in the sky. As you rest here, picture Mars in your mind, a quiet world of rust-red deserts and towering volcanoes, of canyons deeper than imagination and seasons that move with patient slowness. It's a world waiting, watching, holding its secrets close as it circles the distant sun. Now we journey outward, crossing a threshold in our solar system, leaving behind the small, rocky worlds and entering the realm of giants. Between Mars and Jupiter lies the asteroid belt, a river of ancient stones, remnants from the birth of our solar system some 4.6 billion years ago. These are the building blocks that never quite became a planet, prevented by Jupiter's immense gravitational influence from gathering together. They drift in their orbits like a scattered memory, peaceful and patient, waiting in the darkness. And beyond the stellar river, we encounter Jupiter, the king of planets, the largest world in our solar system. Jupiter is so immense that all the other planets combined could fit inside it with room to spare. More than 1,300 Earths could nestle within Jupiter's vast volume, and yet despite this enormousness, Jupiter is surprisingly light for its size. It's made mostly of hydrogen and helium, the same elements that comprise the Sun, giving Jupiter the feel of a star that never quite ignited, a flame that chose instead to remain a gentle giant. Look closely at Jupiter, and you'll see it's wrapped in bands of clouds, stripes of cream and rust and amber that flow around the planet like ribbons on a cosmic gift. These bands are created by powerful winds that race across Jupiter's surface at speeds up to 400 miles per hour, far faster than any hurricane on Earth. Yet from our distance, these violent winds appear serene, creating patterns of such beauty that Jupiter resembles a work of abstract art, painted in earth tones and swirling with eternal motion. The most famous feature on Jupiter is the Great Red Spot, a storm so large that 2 or 3 Earths could fit inside it. This crimson eye has been watching the cosmos for at least 400 years. We know this because astronomers first observed it in the 1600s, and it has persisted ever since. Imagine a storm older than your great-great-great-great-grandparents, a tempest that has been raging since before the American Revolution, before the Enlightenment, spinning counterclockwise in Jupiter's southern hemisphere like a cosmic whirlpool that refuses to calm. And yet, in recent decades, astronomers have noticed the Great Red Spot is slowly shrinking, becoming more circular, as if even this ancient storm is growing tired and preparing, eventually, to rest. Jupiter doesn't journey through space alone. It has at least 95 known moons, a miniature solar system unto itself, a family of worlds each with its own character and story. The four largest, discovered by Galileo in 1610, are called the Galilean moons, Io, Europa, Ganymede, and Callisto. Ganymede holds a special distinction. It's the largest moon in our entire solar system, even larger than the planet Mercury, a moon so substantial it would be considered a planet if it orbited the Sun directly instead of circling Jupiter in devoted attendance. But perhaps the most intriguing of Jupiter's moons is Europa, a world wrapped in ice. Beneath Europa's frozen surface lies an ocean of liquid water, kept warm by the tidal forces generated by Jupiter's powerful gravity. This ocean may be twice the volume of all of Earth's oceans combined, hidden beneath miles of ice, dark and mysterious and potentially harboring life. Scientists dream of one day sending a probe to drill through that ice and explore what lies beneath, to discover if Europa's ocean is empty or if something swims in those eternal depths, unknown and waiting. As Jupiter spins, completing one rotation in just under 10 hours despite its enormous size, it stands as a guardian of the inner solar system, its massive gravity deflecting comets and asteroids that might otherwise threaten Earth. In a way, we owe our existence to Jupiter, this striped giant that watches over us from afar, a celestial protector spinning peacefully in the darkness. Let yourself drift further outward now, past Jupiter's protective embrace, to the sixth planet from the Sun, Saturn, the jeweled crown of our solar system. Even from vast distances, Saturn captivates with its magnificent rings, those ethereal bands of ice and rock that encircle the planet like a cosmic halo. These rings are Saturn's gift to the universe, a reminder that even in the cold darkness of space, there exists extraordinary beauty. Saturn itself is nearly as large as Jupiter, about 760 Earths could fit inside Saturn's volume, yet it holds a remarkable secret. Of all the planets in our solar system, Saturn is the least dense. In fact, if you could find an ocean large enough, Saturn would float on its surface like a giant cosmic beach ball. This is because Saturn, like Jupiter, is composed primarily of hydrogen and helium, but Saturn's composition makes it even lighter, with a density less than that of water. Imagine that, a planet so vast, yet so light it could drift atop an imaginary sea. Those iconic rings, so beautiful from afar, are actually quite thin, in most places only about 30 feet thick, despite stretching over 175,000 miles from edge to edge. If you were to create a scale model where the rings were as thin as a sheet of paper, the paper would need to be about half a mile wide to maintain the same proportions. The rings are made of countless particles, ranging from tiny grains smaller than sand to house-sized chunks of ice and rock, all reflecting sunlight and creating that silvery shimmer we see through our telescopes. Each particle is essentially a tiny moon, following its own orbit around Saturn, together creating an illusion of solid bands. These rings aren't permanent features, They're relatively young in cosmic terms, perhaps only 100 million years old, and they may disappear in another 100 million years. They're temporary jewelry, a brief adornment in Saturn's long existence, like frost on a winter morning that will eventually melt away. Scientists believe the rings may have formed from a moon that ventured too close to Saturn and was torn apart by the planet's gravity, or perhaps from the remnants of comets that collided. Either way, the rings are a reminder that even destruction can create breathtaking beauty. Saturn spins rapidly for such a large planet, completing one rotation in just over 10.5 hours. This rapid rotation causes the planet to bulge at its equator, making Saturn noticeably flattened at its poles. If you could see Saturn from the side, you'd notice it's not quite spherical but slightly squashed, as if the planet is being gently compressed by invisible hands. This bulge is so pronounced that Saturn's equatorial diameter is about 10% larger than its polar diameter, giving the planet an endearingly imperfect shape. Like Jupiter, Saturn hosts a large family of moons. At least 146 known moons orbit this ring giant, each one a small world with its own story. The largest is Titan, a moon larger than the planet Mercury and the only moon in our solar system with a thick atmosphere. Titan's atmosphere is so dense, about 1.5 times denser than Earth's, that it completely obscures the moon's surface from view, wrapping Titan in a perpetual haze of orange and gold. Beneath those hazy skies lie lakes and seas, not of water, but of liquid methane and ethane, making Titan the only world besides Earth known to have stable bodies of liquid on its surface. Rain falls from Titan's clouds, rivers flow across its landscape, and waves lap at alien shores, all in a cycle eerily similar to Earth's water cycle, yet fundamentally different, a parallel version of our own world rendered in methane instead of water. Picture Saturn now as you settle deeper into rest, a pale golden sphere adorned with rings of ice, spinning rapidly through space, surrounded by a family of moons, one of which holds seas beneath orange skies. It's a world of subtle beauty, of quiet majesty, patient and serene in its distant orbit. Our journey carries us now to the outer reaches of the solar system, where the sun appears as little more than a bright star, and the cold grows profound. Here we find Uranus, the seventh planet, a world tilted in the most peculiar way. While most planets spin like tops, with their axes roughly perpendicular to their orbits, Uranus rolls on its side like a ball, its axis tilted at 98 degrees. Imagine a planet lying down as it travels around the Sun, its poles taking turns pointing directly at our distant star. This means that for part of Uranus's year, one pole experiences continuous sunlight for 42 Earth years, while the other endures 42 years of darkness, an endless day followed by an endless night, a cosmic meditation on extremes. Uranus takes 84 Earth years to complete one orbit around the Sun, which means each season on this distant world lasts about 21 years. A spring that stretches across 2 decades, a summer that your children might grow up in, an autumn that seems eternal. Time moves differently out here in the cold darkness, stretched and patient, as if the universe is reminding us that there's no hurry, that everything unfolds in its own perfect rhythm. This ice giant, for Uranus, is classified as an ice giant rather than a gas giant like Jupiter and Saturn, appears as a serene, pale blue-green sphere when viewed through telescopes. The color comes from methane in its atmosphere, which absorbs red light and reflects blue and green wavelengths back into space. It's a gentle color, soothing and cool, like seafoam or mint, giving Uranus an appearance of tranquility. The planet's atmosphere is remarkably calm compared to Jupiter's violent storms or Saturn's winds. Uranus seems to prefer quietude, as if the cold has stilled it into a state of peaceful contemplation. Beneath that calm atmosphere lies something unexpected. Uranus radiates very little heat compared to the other giant planets. While Jupiter, Saturn, and Neptune all emit more heat than they receive from the Sun, leftover warmth from their formation, Uranus releases barely any internal heat at all. It's as if the planet has already cooled to match its environment, finding equilibrium with the cold darkness that surrounds it, content to be exactly what it is without excess or waste. Uranus has at least 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, a delightful literary touch in the cosmic void. Miranda, Ariel, Umbriel, Titania, and Oberon are the 5 largest, each a small frozen world orbiting their tilted parent planet. Miranda, the innermost of the large moons, is particularly fascinating. Its surface is a chaotic patchwork of different terrains, smooth plains next to jagged cliffs, ancient cratered regions beside younger grooved areas. It's as if Miranda was shattered into pieces at some point in its past and then reassembled haphazardly by gravity, a broken moon that put itself back together, scarred but whole. Like Saturn, Uranus also has rings, though they're far fainter and were only discovered in 1977, nearly 200 years after the planet itself was found. These rings are dark and narrow, made of particles much darker than Saturn's bright ice rings, as if Uranus prefers to keep its jewelry subtle and understated. There are 13 known rings, each thin and delicate, circling the planet's equator, which means they appear to stand upright relative to Uranus's orbit, like hoops around a planet lying on its side. They're rings that few people know about, secret adornments for a world content to remain mysterious. Let your mind rest here for a moment with Uranus, this tilted world of pale blue-green, rolling through space in its own unique way, patient and unhurried, taking 84 years to complete what Earth does in one, surrounded by literary moons and dark rings, serene in the profound cold. We venture now to the edge of our planetary system, to Neptune, the 8th and final planet, a world so distant that sunlight takes more than 4 hours to reach it. Neptune orbits the Sun at an average distance of about 2.8 billion miles, so far out that it takes 165 Earth years to complete a single journey around our star. This means that since Neptune was discovered in 1846, it has only completed one full orbit in 2011, just one Neptunian year in all of human history's awareness of its existence. It's a world that teaches us patience on a scale almost beyond comprehension. Despite being the most distant planet, Neptune is not the coldest. That distinction belongs to Uranus. Yet Neptune is still profoundly cold, with temperatures in its upper atmosphere dropping to about -353 degrees Fahrenheit. At these temperatures, the air itself would freeze on Earth, yet Neptune's atmosphere swirls with activity, alive with movement despite the deep cold. It's painted in rich, deep shades of blue, even more vibrant than Uranus, a color so intense it resembles a sapphire floating in the darkness, or the deepest parts of Earth's oceans where sunlight cannot reach. This beautiful blue comes, like Uranus, from methane in the atmosphere, but Neptune appears a deeper, more striking blue. Scientists believe there may be an additional unknown component in Neptune's atmosphere that enhances this color, something we haven't yet identified, a mystery the planet keeps to itself. The winds on Neptune are the fastest in the solar system, screaming across the planet at speeds up to 1,200 miles per hour, nearly supersonic, faster than the speed of sound on Earth. These winds create enormous storm systems that appear and disappear over time, dark spots in the blue atmosphere that astronomers watch with fascination. The most famous of these was the Great Dark Spot, first observed by Voyager 2 when it flew past Neptune in 1989. This massive anticyclonic storm, about the size of Earth, churned in Neptune's southern hemisphere, a dark oval in the bright blue atmosphere. But by the time the Hubble Space Telescope looked for it in 1994, the Great Dark Spot had vanished completely, replaced by other storms in other regions. Neptune's atmosphere is constantly changing, dynamic and restless, as if the planet refuses to remain still, refuses to be fully known. Neptune has at least 16 known moons, the largest of which is Triton, a world of superlatives and mysteries. Triton is the only large moon in our solar system that orbits in the opposite direction of its planet's rotation, a retrograde orbit that tells scientists Triton wasn't born alongside Neptune but was captured by the planet's gravity long ago, a wanderer from elsewhere in the solar system, perhaps from the distant Kuiper belt, now bound forever to Neptune in an eternal dance. Triton is also one of the coldest objects in our solar system, with surface temperatures around -391 degrees Fahrenheit, cold enough that nitrogen freezes solid. Yet despite this extreme cold, Triton is geologically active. When Voyager 2 flew past in 1989, it photographed geysers erupting from Triton's surface, shooting nitrogen gas and dark particles up to 5 miles high. These cryovolcanic eruptions, ice volcanoes, essentially, create dark streaks across Triton's frozen surface, blown by thin winds into patterns that shift over time. It's a reminder that even in the coldest, most distant reaches of our solar system, worlds remain active and alive, that stillness and movement coexist, that change persists even in the frozen dark. Neptune spins relatively quickly for such a large planet, completing one rotation every 16 hours, slightly slower than Jupiter and Saturn but faster than Uranus. As it spins, it emanates more heat than it receives from the distant Sun, internal warmth left over from its formation billions of years ago, slowly radiating into space, a gentle warmth in the profound cold, like embers that refuse to completely fade. Picture Neptune now, this deep blue jewel at the edge of our planetary family, racing with winds we cannot imagine, orbited by a captured moon that erupts ice geysers, spinning steadily through the darkness, patient and eternal. Beyond Neptune lies a realm we are only beginning to understand, a region where our story of planets takes on a different character. Here, in the cold outer darkness, we find Pluto, no longer classified as a planet since 2006, but reclassified as a dwarf planet, a distinction that sparked passionate debates among astronomers and the public alike. Yet Pluto remains beloved, a small world that captured our hearts long before we truly knew what it looked like. For decades, Pluto existed in our imagination as little more than a fuzzy dot in our most powerful telescopes, mysterious and distant, waiting patiently to reveal itself. Pluto orbits the Sun at an average distance of about 3.7 billion miles, though its orbit is so elliptical, so elongated, that sometimes it actually comes closer to the Sun than Neptune does. For 20 years of Pluto's 248-year orbit, from 1979 to 1999, Pluto was technically the 8th planet from the Sun, not the 9th, as it traveled through the inner part of its stretched-out path. It's a world that refuses to follow the same rules as the others, carving its own unique journey through space at an angle tilted 17 degrees from the plane where the other planets orbit, as if Pluto prefers to see things from a different perspective. When NASA's New Horizons spacecraft finally reached Pluto in 2015, after a journey of more than 9 years, it revealed a world far more complex and beautiful than anyone had imagined. Pluto's surface is a wonderland of geological features, vast plains of nitrogen ice, water-ice mountains rising up to 11,000 feet high, and a distinctive heart-shaped region called Tombaugh Regio, named after Clyde Tombaugh, who discovered Pluto in 1930. This heart, visible in the images sent back to Earth, seemed almost intentional, as if Pluto was greeting us with affection after our long journey to meet it. Pluto has 5 known moons, the largest being Charon, which is so large relative to Pluto, about half Pluto's diameter, that the two worlds orbit a common point in space between them, like a pair of dancers holding hands and spinning together. Astronomers sometimes call this a binary system rather than a planet and moon, two partners locked in an eternal waltz. Charon is tidally locked to Pluto, meaning the same side of Charon always faces Pluto, and Pluto is also tidally locked to Charon. If you stood on the right place on Pluto's surface, Charon would hang in the same spot in the sky forever, never rising or setting, a permanent companion in the darkness. The temperature on Pluto plunges to about -375 degrees Fahrenheit, cold enough that the nitrogen in its thin atmosphere periodically freezes and falls to the surface as snow, accumulating over the ages. When Pluto is closest to the Sun in its elliptical orbit, some of this frozen nitrogen sublimates, turns directly from solid to gas, creating a temporary atmosphere. But as Pluto moves farther from the Sun, the atmosphere freezes again and snows back down to the surface. Pluto breathes, in a sense, inhaling and exhaling over the course of its long orbit, its atmosphere expanding and contracting like slow, patient breaths taken across centuries. New Horizons also discovered that Pluto has a subsurface ocean, hidden beneath miles of ice, liquid water kept from freezing by radioactive decay in Pluto's core and the insulating properties of an outer layer of gas hydrates. Even here, at the edge of the solar system, where the Sun appears as nothing more than a bright star, where darkness and cold seem absolute, there exists liquid water, the essence of life as we know it. It's a humbling reminder that the universe is full of unexpected warmth, hidden depths, secret oceans beneath frozen surfaces, waiting to be discovered. Let yourself drift now with Pluto, this small world at the boundary of our solar system, heart-shaped and welcoming, dancing with its companion Charon through the darkness, breathing its atmosphere across centuries, holding an ocean beneath its icy skin, patient and enduring. Our journey now takes us back inward, returning from the outer darkness toward the warmth of the inner solar system, but with a different perspective, a new appreciation for the cosmic dance we've witnessed. As we travel, let's pause to consider something miraculous about our solar system, the way each planet maintains its orbit with such precision, such reliability, that we can calculate their positions thousands of years into the past or future with extraordinary accuracy. This celestial clockwork operates according to laws discovered by Johannes Kepler in the early 1600s, refined by Isaac Newton later that century. Each planet follows an elliptical path, sweeping through space in a pattern so regular that ancient civilizations used planetary movements to mark time, to plant crops, to navigate across oceans. The planets have been keeping this schedule for over 4.6 billion years, since the solar system formed from a spinning cloud of gas and dust, a cosmic nebula that collapsed under its own gravity and gave birth to the Sun and everything that orbits it. In those earliest days, the solar system was a chaotic place, planets migrating inward and outward, colliding and merging, fragments smashing together to build larger worlds. Earth itself was struck by a Mars-sized body called Theia about 4.5 billion years ago, a collision so tremendous that it vaporized rock and sent debris into orbit around our young planet. That debris eventually coalesced to form the Moon, meaning our lunar companion was born from Earth itself, made of the same material, a child of catastrophe that became our steady nighttime companion. The violence of creation giving way to billions of years of gentle, reliable presence. As we pass back through the realm of the gas giants, consider their role as cosmic guardians. Jupiter and Saturn, with their immense gravitational fields, act like shields for the inner solar system, deflecting or capturing comets and asteroids that might otherwise threaten Earth. Some scientists estimate that without Jupiter's protective influence, Earth might experience impacts from large objects up to 1,000 times more frequently than it does. We exist, in part, because these giant planets stand watch in the outer solar system, silent sentinels who have protected us for eons without our knowing. The asteroid belt, which we pass again on our journey inward, contains millions of rocky bodies, yet if you were to somehow gather all the asteroids together, their combined mass would be less than 4% of the Moon's mass. Despite appearing crowded in diagrams, the asteroid belt is actually mostly empty space. You could fly through it and likely never come close to hitting anything. NASA has sent numerous spacecraft through the asteroid belt without incident, gliding through vast distances where rocky fragments drift in peaceful isolation, each one a time capsule from the solar system's formation, unchanged for billions of years. Speaking of time, consider this: light from the Sun takes about 8 minutes and 20 seconds to reach Earth. This means when you feel sunlight on your face, you're feeling warmth that left the Sun more than 8 minutes ago. You're touching the past, basking in photons that began their journey before you decided to step outside. To reach Pluto, that same sunlight takes over 5.5 hours, arriving at a world where the Sun appears 1,600 times dimmer than it does from Earth, bright enough to see by, but creating a twilight realm where high noon feels like Earth's dusk. And here's something beautiful to contemplate as you settle deeper into rest. Every atom in your body, every particle that makes you who you are, was forged in the heart of a star that existed long before our Sun was born. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created by nuclear fusion in ancient stars that lived, burned brightly, and then exploded as supernovae, scattering their enriched material into space. That material eventually became part of the cloud that formed our solar system. You are made of stardust, quite literally, connected to the cosmos in the most intimate way possible. As we drift back toward the inner solar system, let's turn our attention to something we've passed by but haven't yet properly explored: the dwarf planets and small worlds that populate the spaces between and beyond the planets we know. Beyond Neptune lies a vast region called the Kuiper Belt, a disk-shaped zone extending from about Neptune's orbit outward to nearly 50 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles, so the Kuiper Belt stretches across billions of miles of space, populated by countless icy bodies, remnants from the solar system's formation that never gathered into full planets. The Kuiper Belt is home to several dwarf planets besides Pluto. There's Eris, discovered in 2005, which is slightly smaller than Pluto but more massive, denser. It was Eris's discovery that ultimately led to Pluto's reclassification, as astronomers realized the outer solar system contained many Pluto-sized worlds. Then there's Makemake, named after the creation deity of the Rapa Nui people of Easter Island, a reddish world about 2/3 Pluto's size. And Haumea, one of the strangest objects in our solar system, a dwarf planet that spins so rapidly, completing one rotation every 4 hours, that it's been stretched into an ellipsoid shape, like a cosmic football tumbling through space. Haumea even has its own ring system, making it one of the smallest known objects to possess rings. These distant worlds remind us that our solar system doesn't end neatly at Neptune. It extends outward in layers, like an onion, each region containing different populations of objects. Beyond the Kuiper belt lies the scattered disk, and beyond that, the Oort cloud, a theoretical sphere of icy objects surrounding our entire solar system, extending perhaps halfway to the nearest star. The Oort cloud may contain trillions of comets, frozen wanderers waiting patiently in the dark, some of which occasionally get nudged by gravitational perturbations and begin the long fall inward toward the sun, growing tails as they warm, becoming the spectacular comets we occasionally see from Earth. Let's return now to Mercury, our starting point, but with deeper understanding. Mercury, despite being the closest planet to the Sun, has water ice hidden in permanently shadowed craters at its poles. These craters never receive direct sunlight, their floors exist in eternal darkness, cold enough that water ice can persist despite Mercury's scorching daytime temperatures. Spacecraft have detected this ice using radar, revealing deposits that may be several meters thick. It's a beautiful paradox, ice existing on the hottest planet in our solar system, protected by shadows that have lasted for billions of years. Venus, too, holds surprises we haven't yet mentioned. Despite its crushing atmospheric pressure and hellish temperatures, Venus has snow, not water snow, but metallic snow made of bismuthinite and galena compounds. This exotic precipitation forms in the cooler highlands above 8,200 feet elevation, where temperatures drop just enough for these metallic compounds to condense and fall, coating the mountaintops in a reflective frosting that can be detected in radar images. It's snow unlike anything on Earth, glittering metallic crystals settling on peaks that rise through the sulfuric acid clouds. And Mars whispers of water in its past. The planet's surface is carved with ancient river valleys, outflow channels, and what appear to be dried lake beds. Billions of years ago, Mars likely had a thicker atmosphere and liquid water flowing across its surface, perhaps even oceans in its northern lowlands. The water disappeared as Mars lost most of its atmosphere, stripped away by solar wind because Mars lacks a strong magnetic field to protect it, but evidence suggests water still exists there, locked in ice caps and buried deposits. In 2018, scientists discovered a lake of liquid water beneath Mars's southern ice cap, kept liquid by dissolved salts and the pressure of ice above it. Mars dreams of its watery past, holding on to what remains beneath its dusty surface. Rest now with these thoughts: ice hiding in Mercury's shadowed craters, metallic snow on Venus's peaks, ancient water whispering through Mars's canyons, distant dwarf planets tumbling through the dark beyond Neptune, and comets sleeping in the Oort cloud, waiting for their moment to fall sunward and blaze across our skies. Let us turn our attention now to something we see every night but perhaps don't fully appreciate: our moon, Earth's constant companion. The moon is slowly drifting away from us, as we mentioned earlier, but this creates a beautiful consequence: total solar eclipses, those moments when the moon passes directly in front of the sun and casts its shadow upon Earth. What makes these eclipses so spectacular is an extraordinary cosmic coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away, which means from Earth's surface, they appear to be almost exactly the same size in our sky. This perfect sizing is temporary in cosmic terms. Billions of years ago, when the moon was closer, it would have appeared larger and eclipses would have been less precise, the moon covering the sun completely with room to spare. Billions of years in the future, when the moon has drifted even farther, it will appear too small to completely cover the sun, and total solar eclipses will no longer occur, only partial and annular eclipses will be possible. We live in a precious window of time, perhaps a few 100 million years in duration, when the geometry aligns perfectly, allowing us to witness the sun's corona dancing around the moon's silhouette during those few minutes of totality. The moon's influence on Earth extends far beyond eclipses. Its gravitational pull creates our tides, but it also does something more subtle: it stabilizes Earth's axial tilt. Without the moon, Earth's tilt would vary chaotically over millions of years, ranging from nearly 0 degrees to 85 degrees or more, creating wildly unpredictable climate swings. Mars, which has no large moon to stabilize it, experiences exactly this problem. Its axial tilt has varied between 15 and 35 degrees over millions of years, causing dramatic climate shifts. Our moon keeps Earth steady, maintaining the roughly 23.5-degree tilt that gives us our regular seasons, our predictable climate, the stability that allowed complex life to evolve. Return with me now to Jupiter, and let's explore one of its most fascinating moons more deeply, Io, the innermost of the 4 Galilean moons. Io is the most volcanically active body in our entire solar system, with hundreds of active volcanoes constantly reshaping its surface. These aren't small volcanoes. Some of Io's volcanic plumes shoot material up to 250 miles above the surface, high enough that if they occurred on Earth, they would reach into space. The surface of Io is constantly being renewed, buried under new lava flows, which means Io has no impact craters. Any craters that form are quickly covered over by volcanic activity, giving Io the youngest surface of any solid body in the solar system. This intense volcanism is powered by tidal heating. Jupiter's immense gravity pulls on Io, but so do the other Galilean moons, Europa and Ganymede. These competing gravitational forces squeeze and stretch Io as it orbits, generating friction in the moon's interior that melts rock and drives the volcanic activity. Io glows with the heat of this internal furnace. In infrared images, you can see hot spots across its surface where lava lakes bubble and fountains of molten rock spray into the thin atmosphere. It's a world painted in yellows, oranges, and reds, colored by sulfur and sulfur dioxide, looking less like a moon and more like a cosmic pizza, as some astronomers have affectionately described it. Europa, by contrast, is a world of ice and hidden depths. Its surface is crisscrossed with long, linear features called lineae, cracks in the ice that have been filled with darker material from below. Scientists believe Europa's icy shell is between 10 and 15 miles thick, floating atop an ocean that may be 40 to 100 miles deep. That means Europa's ocean could contain more than twice the water in all of Earth's oceans, despite Europa being smaller than our moon. The ice shell is constantly renewing itself. Europa has very few impact craters, suggesting the surface is young, perhaps only 20 to 180 million years old, constantly recycled as the ice cracks, shifts, and new ice forms from below. Tidal heating keeps Europa's ocean liquid, just as it powers Io's volcanoes, though Europa experiences less intense tidal forces and thus remains frozen on the surface while liquid beneath. Future missions are planned to Europa, spacecraft that will orbit the Moon, analyze its ice with radar, perhaps even taste the plumes of water vapor that erupt from cracks in the surface, searching for signs of organic molecules, hints that something might live in that dark ocean beneath the ice. Let your mind rest with Europa now, imagining that vast hidden ocean, dark and cold but potentially alive, protected beneath miles of ice, a secret sea where unknown creatures might swim through eternal night. As we continue our gentle voyage through the solar system, let's turn our attention to Saturn's moon Enceladus, a small world only 310 miles in diameter, small enough to fit within the borders of Texas, yet one of the most exciting discoveries in planetary science. Enceladus has a smooth, bright surface of nearly pure water ice, making it one of the most reflective bodies in the solar system. It reflects almost 100% of the sunlight that hits it, appearing as a brilliant white jewel in Saturn's family of moons, gleaming like fresh snow on a winter morning. But Enceladus holds an extraordinary secret. In 2005, the Cassini spacecraft discovered enormous geysers erupting from cracks near the Moon's south pole, plumes of water vapor, ice particles, and organic molecules shooting more than 60 miles into space. These geysers are so powerful, so persistent, that they create one of Saturn's rings. The faint E ring is actually made of ice particles from Enceladus, spread along the Moon's orbit like a trail of breadcrumbs. Enceladus is actively feeding Saturn's ring system, constantly replenishing it with fresh ice from its interior. Beneath Enceladus's icy shell lies a global ocean of liquid water, kept warm by tidal heating from Saturn's gravity. Scientists have detected molecular hydrogen in the plumes, a sign that hot water is reacting with rock on the ocean floor, the same kind of chemical reactions that support life in Earth's deep ocean hydrothermal vents. Enceladus has all the ingredients for life as we know it: liquid water, organic molecules, and chemical energy sources. The possibility that something might live in that subsurface ocean, swimming in the dark beneath 10 miles of ice, orbiting Saturn, is one of the most tantalizing questions in astrobiology. Now let's return to Saturn itself and contemplate one of its most mysterious features, the hexagonal storm at its north pole. This isn't a metaphor or an approximation, it's an actual hexagon, a six-sided jet stream wider than Earth, with each side stretching about 9,000 miles. Inside this hexagon spins a massive hurricane-like vortex, with winds reaching 330 miles per hour. The hexagon has persisted for at least 30 years. We've been observing it since the Voyager missions in the 1980s, and it likely existed long before that. Scientists still don't fully understand why this storm takes a hexagonal shape. Laboratory experiments suggest it's related to the interaction of different wind speeds at different latitudes, but Saturn's hexagon remains one of the solar system's elegant mysteries. At Saturn's south pole, there's another massive vortex, though this one is circular rather than hexagonal. This southern hurricane has a well-defined eye, similar to hurricanes on Earth, but it's about 1,250 miles across, large enough to swallow most of the United States. Inside the eye, the atmosphere is relatively calm, surrounded by walls of clouds rising dozens of miles high, spinning at tremendous speeds. Saturn shows us that atmospheric dynamics can create structures both familiar and utterly alien, patterns that persist for decades or longer, storms that dwarf anything Earth experiences. Speaking of Earth's atmosphere, let's appreciate something we often take for granted: our magnetic field. Earth's liquid iron core, spinning as the planet rotates, generates a magnetic field that extends far into space, creating a protective bubble called the magnetosphere. This invisible shield deflects most of the solar wind, the stream of charged particles constantly flowing from the sun, protecting our atmosphere from being stripped away. When solar wind particles do penetrate near the poles, they interact with our atmosphere to create the aurora borealis and aurora australis, the northern and southern lights, curtains of green, pink, and violet dancing across the polar skies. Other planets have auroras too. Jupiter's auroras are the most powerful in the solar system, powered by its enormous magnetic field and enhanced by particles from volcanic Io. Saturn, Uranus, and Neptune all have auroras, each unique to their particular magnetic field configurations. Even Mars has localized auroras. Despite lacking a global magnetic field, these occur over regions of ancient magnetized crust, ghostly lights flickering above remnants of the magnetic field Mars lost billions of years ago, a memory of what once was. Rest now with these images. Enceladus spraying ice into space, feeding Saturn's rings, harboring a hidden ocean beneath its brilliant surface. Saturn's hexagonal storm spinning at its north pole, a geometric mystery persisting for decades. Earth's magnetic shield protecting us, creating auroras that dance in polar skies, each world with its own wonders, its own stories written in ice and storms and magnetic fields. Let us drift now to contemplate the varying lengths of days across our solar system, for time itself moves differently on each world. We've mentioned that Mercury's day lasts 176 Earth days, and Venus rotates so slowly that its day exceeds its year. But consider Jupiter, that massive giant. Despite being over 1,300 times Earth's volume, it completes one rotation in just under 10 hours. This rapid spin causes Jupiter's equator to bulge outward noticeably, and it creates the powerful jet streams that form those beautiful cloud bands we see wrapping around the planet. The fastest rotation in our solar system belongs to Haumea, that egg-shaped dwarf planet spinning once every 4 hours, but among the major planets, Jupiter holds the record. This rapid rotation also generates Jupiter's powerful magnetic field, the largest planetary magnetic field in our solar system, extending millions of miles into space. If we could see Jupiter's magnetosphere with our eyes, it would appear several times larger than the full moon in Earth's sky, despite Jupiter being so far away. The planet sweeps up charged particles in this enormous magnetic bubble, creating intense radiation belts that would be lethal to unprotected spacecraft and humans. Neptune, meanwhile, spins once every 16 hours, giving it a day about 2/3 the length of Earth's. But here's something curious. Neptune's magnetic field is tilted 47 degrees from its rotation axis and offset from the planet's center. This creates a wildly complex magnetic field that wobbles as the planet rotates, unlike Earth's relatively stable, aligned field. Uranus shares this peculiarity. Its magnetic field is also tilted at 59 degrees and offset from center. Scientists believe this might be because both ice giants have their magnetic fields generated in a slushy layer of water, ammonia, and methane deep inside, rather than in a metallic core like Earth's field. Return with me now to our moon, and consider the footprints left by Apollo astronauts between 1969 and 1972. Those footprints remain virtually unchanged on the lunar surface. The Moon has no atmosphere, no wind or weather to erode them away, no rain to wash them clean. Without these forces, the footprints, along with the tracks from the lunar rovers, the flags planted in the dust, the equipment left behind, will persist for millions of years, preserved in the airless vacuum like fossils, testaments to humanity's first steps on another world. In a sense, those footprints are eternal, or as close to eternal as anything humans have created can be. The Moon's surface is covered in a fine powder called regolith, created by billions of years of micrometeorite impacts. Without an atmosphere to burn them up, even tiny particles strike the Moon's surface at cosmic velocities, gradually pulverizing the rock into an ever finer dust. This regolith is between 10 and 50 feet deep in most places, a powdery blanket that took eons to create. The Apollo astronauts described it as having the consistency of talcum powder, clinging to everything it touched, smelling oddly like spent gunpowder, a scent created by the reaction of lunar dust with oxygen inside their spacecraft. Let's travel now to Venus and contemplate another temporal oddity. Because Venus rotates so slowly and in the opposite direction from most planets, the sun rises in the west and sets in the east, and the time between sunrises is 117 Earth days. But here's what makes it even stranger: if you were standing on Venus's equator, protected somehow from the crushing pressure and searing heat, and you started walking westward at a brisk pace of about 4 miles per hour, you could theoretically keep pace with the sun, keeping it fixed in the same position in the sky, experiencing either eternal noon or eternal midnight depending on when you started. Venus rotates so slowly that human walking speed can match its rotation, turning a simple walk into a journey through frozen time. Breathe slowly now, and imagine these different measures of time: Jupiter spinning twice during an Earth day, Neptune's tilted magnetic field wobbling as it turns, footprints on the Moon waiting in stillness for millions of years, Venus rotating so slowly you could walk alongside the Sun. Let us contemplate now the colors of our solar system, for each world presents its own unique palette to the cosmos. We've spoken of Neptune's deep sapphire blue and Uranus's pale seafoam, but consider Mars more closely. That rusty red color, so distinctive and familiar, varies across the planet's surface. Some regions appear almost salmon pink, others dark brown or tan, and the polar ice caps gleam white against the rust. During global dust storms, which can envelope the entire planet for months, Mars turns a uniform butterscotch hue, the dust suspended in the thin atmosphere creating a veil that obscures all surface features. These planet-wide dust storms occur roughly every 3 to 4 Martian years, transforming the entire world into a hazy, monochromatic sphere. Mars's sky, when clear, appears butterscotch or pinkish tan during the day, opposite to Earth's blue sky, because the fine dust particles suspended in the atmosphere scatter light differently than our nitrogen and oxygen molecules do. But here's something wonderfully poetic: Martian sunsets are blue. As the sun drops toward the horizon, the dust scatters the red wavelengths of light, allowing the blue to pass through more directly. So on Mars, you would watch a blue sun sink below a dusty pink horizon, an inverse of Earth's experience, where our blue sky gives way to red and orange sunsets. Jupiter's colors tell stories of chemistry and depth. The lighter bands, called zones, are regions of rising gas, cooler and higher in the atmosphere, composed mainly of ammonia ice crystals that appear white or cream-colored. The darker bands, called belts, are regions where gas descends, warmer and lower, revealing deeper layers tinged with compounds that might include sulfur, phosphorus, and complex organic molecules. The exact chemistry that creates Jupiter's browns, tans, and oranges remains somewhat mysterious. Scientists call these unknown compounds chromophores, color makers whose identities we're still investigating. Saturn's colors are more subtle than Jupiter's, creating a softer, more pastel appearance. The planet appears pale gold or cream, its bands muted compared to Jupiter's dramatic contrasts. This is partly because Saturn is colder than Jupiter, being farther from the Sun, which means a thicker haze layer of ammonia ice crystals overlays the deeper, more colorful clouds. It's as if Saturn wears a gauzy veil, softening and diffusing its colors, giving it a dreamy, watercolor quality. The hexagonal storm at Saturn's north pole appears blue in some wavelengths, creating a striking geometric blue feature against the golden planet. Now let's visit Mercury again, and explore its surface in detail. Mercury is covered with billions of impact craters, testimony to 4.5 billion years of bombardment. But unlike the Moon's surface, which is predominantly dark gray, Mercury shows a wider range of tones, from light gray to darker regions, with some areas appearing almost bluish in color-enhanced images. The largest impact basin on Mercury is called Caloris Basin, spanning about 960 miles across, large enough to contain the state of Texas. When the asteroid or comet that created Caloris slammed into Mercury, the impact was so violent that it created shockwaves that traveled through the entire planet. On the exact opposite side of Mercury from Caloris Basin, there's a region of chaotic, jumbled terrain called weird terrain, created when those shockwaves converged and disrupted the surface. It's as if the impact literally rang Mercury like a bell, the vibrations traveling through the planet and breaking the surface on the far side. Mercury also has something called hollows, thousands of bright, irregular depressions scattered across the planet, particularly inside craters. These hollows are thought to form when volatile materials buried in Mercury's crust are exposed to the vacuum of space and the intense solar radiation, causing them to sublimate away and leave behind these bright, shallow pits. They give Mercury's surface a distinctive appearance in high-resolution images, as if the planet is slowly evaporating in the intense heat, revealing brighter material beneath like hidden treasures emerging from the dust. Let these colors wash over you now: blue Martian sunsets under pink skies, Jupiter's cream and rust and orange bands, Saturn's soft golden glow veiled in ammonia haze, Mercury's gray surface dotted with bright hollows. Each world painted in its own impossible palette, waiting silently in space. Let us journey outward once more to explore the rings of our solar system in greater detail, for these delicate structures tell stories of gravity, collision, and cosmic artistry. Saturn's rings, the most magnificent of all, are divided into several main sections, each designated by a letter: the A ring, B ring, C ring, and others, named in the order they were discovered rather than their position. Between the A and B rings lies a gap called the Cassini division, about 2,900 miles wide, a space kept clear by the gravitational influence of Saturn's moon Mimas, whose orbit creates a resonance that sweeps particles out of this region. Within the rings themselves are thousands of smaller gaps and waves, some created by tiny moonlets embedded within the rings themselves, others by gravitational resonances with Saturn's many moons. Some of these moonlets, called propeller moons because of the distinctive patterns they create, are only about 300 feet across, roughly the size of a football field, yet they clear gaps in the rings and create wakes in the ice particles around them, like boats moving through water. The Cassini spacecraft discovered hundreds of these propeller features, each one evidence of a small moon sculpting its environment. Saturn's rings are incredibly thin relative to their width. If you created a scale model where the rings were the thickness of a sheet of paper, they would stretch for nearly half a mile. Yet despite their thinness, the rings contain an enormous amount of material. Scientists estimate the ring's mass is about 40% that of Saturn's moon Mimas, which itself is about 250 miles across. All that ice and rock, spread into a disk so thin you could almost see through it edge-on, yet stretching across hundreds of thousands of miles. Jupiter's rings, by contrast, are faint and dusty, composed primarily of small particles knocked off Jupiter's innermost moons by micrometeorite impacts. These rings were unknown until the Voyager 1 spacecraft discovered them in 1979. They're so faint they can't be seen from Earth with ordinary telescopes. Jupiter has 4 main ring components: a thick inner torus of particles, a main ring, and 2 wide, gossamer rings. These gossamer rings are made of material from the moons Amalthea and Thebe, stretched along these moons' orbits, creating faint sheets of dust that extend far from Jupiter. Uranus's rings are darker and narrower than Saturn's, made of material that's among the darkest in the solar system, reflecting only about 2% of the light that hits them, making them appear almost charcoal black. The particles in Uranus's rings range from dust size to perhaps 20 feet across, and the rings are interspersed with clear gaps, creating a structure of alternating darkness and emptiness. Because Uranus is tilted on its side, its rings appear to stand upright, circling the planet's equator like hoops around a wheel lying flat. Neptune's rings are perhaps the most unusual. They're not uniform but contain bright clumps of material called ring arcs. These arcs are regions where ring particles bunch together, creating brighter sections within the otherwise faint rings. The main ring arcs are named Liberté, Égalité, Infraternité, Liberty, Equality, and Fraternity, after the motto of the French Revolution, honoring France's contribution to Neptune's discovery. Scientists aren't entirely certain why these arcs form and remain stable instead of spreading out evenly around Neptune, though they suspect the gravitational influence of Neptune's moon Galatea plays a role, shepherding the particles into clumps. All these ring systems are transient in cosmic time. Saturn's rings may only be 100 million years old and might disappear in another 100 million years, a brief flourish of beauty in the planet's multi-billion-year existence. The other ring systems are likely even younger, perhaps replenished constantly by collisions and impacts. We are fortunate to live in an era when these rings exist, when Saturn wears its crown of ice, when these delicate structures catch sunlight and cast shadows across their parent planets. Close your eyes and picture these rings now: Saturn's bright sheets of ice stretched impossibly thin, Jupiter's faint dusty halos, Uranus's dark hoops standing upright, Neptune's mysterious arcs bunched and bright, all of them temporary jewelry, cosmic ornaments that will one day fade, but for now remain, turning slowly in the eternal darkness. Let us now contemplate the concept of seasons across different worlds, for while Earth's seasonal rhythm feels natural and inevitable to us, each planet experiences the passage of time in its own unique way. We know that Earth's seasons are caused by our planet's 23.5-degree axial tilt. As we orbit the Sun, different hemispheres receive more direct sunlight at different times of year, creating the gentle cycle of spring, summer, autumn, and winter that has governed life on our planet for billions of years. But consider Uranus again, that sideways planet with its 98-degree tilt. During Uranus's 84-year orbit, each pole spends 42 years in continuous sunlight, followed by 42 years in continuous darkness. Imagine being born on Uranus's North Pole during polar summer. You would be middle-aged before you experienced your first sunset, and elderly before you saw sunrise again. The seasons on Uranus aren't subtle transitions but dramatic transformations, entire human lifetimes spent in either day or night, with only the equatorial regions experiencing something resembling normal day-night cycles. When Voyager 2 flew past Uranus in 1986, the planet's south pole was pointed almost directly at the Sun, creating what astronomers call southern summer solstice. The entire southern hemisphere was bathed in sunlight while the north remained in darkness. Scientists expected to see dramatic temperature differences between the sunlit and dark hemispheres, but surprisingly, Uranus's atmosphere shows remarkably uniform temperatures. The heat somehow redistributes around the planet, carried by winds we don't fully understand, creating an almost inexplicable thermal equilibrium despite the extreme illumination differences. Neptune, despite being farther from the Sun than Uranus, paradoxically has more dramatic weather and more visible storm systems. Scientists believe this is because Neptune generates more internal heat than Uranus does. Neptune radiates about 2.6 times more energy than it receives from the Sun, while Uranus barely radiates any excess heat at all. This internal warmth drives Neptune's powerful atmospheric circulation, creating those supersonic winds and massive storm systems we discussed earlier. It's as if Neptune has a furnace inside, keeping it active and dynamic, while Uranus has cooled into a state of quiet uniformity. Return with me to Earth, and consider our axial tilt from a different perspective. That 23.5-degree tilt isn't fixed, it actually wobbles very slowly in a cycle called precession, taking about 26,000 years to complete one wobble. Right now, Earth's north polar axis points roughly toward Polaris, the North Star, which is why Polaris appears stationary in the northern sky while other stars wheel around it. But 5,000 years ago, Polaris wasn't the pole star, a different star held that position. And 13,000 years from now, the star Vega will become our new pole star as Earth's axis precesses to point in a different direction. This precession also affects our seasons over millennia. Currently, Earth is closest to the Sun in early January, during Northern Hemisphere winter, and farthest in early July, during Northern summer. This means northern winters are slightly milder and summers slightly cooler than they would be otherwise. The distance effect partially moderates the tilt effect. But in about 13,000 years, due to precession, this will reverse. Earth will be closest to the Sun during northern summer and farthest during northern winter, making northern hemisphere seasons more extreme. These slow cycles of precession contribute to long-term climate patterns, including ice ages, weaving together orbital mechanics and climate in an elegant dance spanning tens of thousands of years. Breathe deeply now, and imagine these vast cycles: Uranus's 42-year seasons of light and darkness, Neptune's internal warmth driving storms across frozen clouds, Earth's axis slowly precessing through the stars, pointing to different pole stars across millennia, our seasons gradually shifting in intensity over thousands of years, time moving at scales both intimate and incomprehensibly vast. Let us explore now the volcanic worlds of our solar system, for fire and ice take many forms across these distant realms. We've spoken of Io's spectacular volcanism, but consider the scale more deeply. Io resurfaces itself completely every million years or so, burying its own history under layer upon layer of new lava and sulfurous deposits. The volcanic plumes we see erupting from Io aren't made of molten rock alone. Some are primarily sulfur dioxide, which exists as a solid frost on Io's surface at temperatures around -240 degrees Fahrenheit, but vaporizes explosively when heated by volcanic activity beneath. The largest volcano on Io is called Patera, a volcanic depression about 125 miles across containing a lava lake so vast and active that it's one of the brightest infrared sources in the entire solar system, visible even from Earth with sensitive instruments. Patera doesn't erupt in the way we think of volcanic eruptions. Instead, its lava lake periodically overturns, with cooled crust on the surface breaking apart and sinking while fresh molten lava wells up from below. This overturn happens roughly every 400 to 600 days in a predictable cycle, creating a rhythmic brightening visible to astronomers billions of miles away. On Earth, we have about 1,500 potentially active volcanoes on land, and many more beneath the oceans along mid-ocean ridges. But Earth's volcanism is gentle compared to Io. Our most powerful eruptions pale beside the continuous, planet-wide volcanic activity of Jupiter's innermost large moon. Yet Earth's volcanism has been essential to life, releasing gases that formed our atmosphere, including the water vapor that eventually became our oceans. Without volcanic activity recycling materials through plate tectonics, Earth would be a very different, likely lifeless world. Venus has more volcanoes than any other planet in our solar system. Over 1,600 major volcanoes have been identified on its surface, and there may be 1 million or more smaller volcanic features. Most of these volcanoes appear to be dormant now, but there's evidence that some may still be active. In 2020, scientists reported finding fresh lava flows that appear to be less than a few years old, suggesting Venus remains volcanically active today. The planet's thick atmosphere makes it difficult to observe the surface directly, but radar mapping from spacecraft like Magellan has revealed a landscape dominated by volcanic features, shield volcanoes, lava plains, and strange circular features called coronae, which may be created by rising plumes of hot material from Venus's mantle. Mars, too, has volcanic features that dwarf anything on Earth. Beyond Olympus Mons, which we've discussed, there's an entire volcanic region called the Tharsis Rise, a massive plateau elevated about 6 miles above the average Martian surface and stretching over 2,500 miles across, roughly the size of North America. This region contains several enormous shield volcanoes in addition to Olympus Mons, including Ascrius Mons, Pavonis Mons, and Arcreus Mons, all standing between 11 and 14 miles high. The sheer mass of the Tharsis Rise actually deformed Mars's shape, creating a bulge that affected the planet's rotation and may have shifted Mars's polar axis in the distant past. These Martian volcanoes appear to have been active relatively recently in geological terms. Some lava flows may be only a few million years old, which is young for a planet billions of years old. Mars lacks plate tectonics, so volcanoes remain over their hotspots for billions of years, building up into these enormous structures rather than creating chains of smaller volcanoes as the crust moves over the hotspot, as happens in Hawaii on Earth. Olympus Mons may have been erupting on and off for over 100 million years, slowly growing to its current immense size, layer by layer, eruption by eruption, while the Martian surface remains stationary beneath it. Rest now with these images of fire across the solar system, Io's lava lake overturning in rhythmic cycles, Venus's surface dotted with over 1 million volcanic features, Mars's enormous shield volcanoes built up over hundreds of millions of years, Earth's gentle volcanism creating the atmosphere that sustains us, each world shaped by internal heat rising to the surface, transforming landscapes, creating new ground. Let us turn our thoughts now to the moons that orbit in unusual ways, defying the expected patterns of celestial mechanics. Most moons orbit their planets in the same direction that the planet rotates, traveling in circular or nearly circular paths around the planet's equator. But some moons rebel against this order, and their stories reveal the chaotic history of our solar system's formation. We've mentioned Neptune's Triton and its retrograde orbit, moving opposite to Neptune's rotation, which tells us Triton was captured from elsewhere rather than forming alongside Neptune. But Triton's story becomes even more fascinating when we consider its fate. Triton is slowly spiraling inward toward Neptune, drawn closer by tidal forces with each orbit. In perhaps 3.6 billion years, Triton will cross what's called the Roche limit, the distance at which Neptune's gravity will overcome Triton's own gravity holding it together. When this happens, Triton will be torn apart, shredded by tidal forces, and its fragments will spread out to form a magnificent ring system around Neptune, far more spectacular than the faint rings Neptune has today. Imagine that distant future, Neptune adorned with rings rivaling or surpassing Saturn's, made not of ancient material from the solar system's formation but from a moon that once orbited intact, a memorial to Triton written in orbiting ice and rock. And eventually, over billions more years, those ring particles will spiral down into Neptune's atmosphere and disappear, leaving no trace that Triton ever existed except perhaps in the geological record of Neptune's remaining moons. Saturn has a moon called Phoebe that also orbits in retrograde, taking about 550 days to complete one orbit at a distance of about 8 million miles from Saturn, much farther than Saturn's other major moons. Phoebe is dark, irregular, and heavily cratered, quite different from Saturn's inner moons. Like Triton, Phoebe was almost certainly captured, probably a wanderer from the Kuiper belt that ventured too close to Saturn and was snared by the giant planet's gravity. Phoebe itself creates a ring, though not in the way you might imagine. Phoebe is constantly being struck by micrometeorites, which knock dark dust particles off its surface. These particles spread along Phoebe's orbit, creating an enormous, tenuous ring of dark material that extends from about 3.7 million miles to 7.4 million miles from Saturn, a ring so large and diffuse it wasn't discovered until 2009, when the Spitzer Space Telescope detected it in infrared light. This Phoebe ring may solve a long-standing mystery about Saturn's moon Iapetus. Iapetus is one of Saturn's strangest moons. One hemisphere is bright white ice, while the other is dark as asphalt, giving it a distinctive two-toned appearance like a cosmic yin-yang symbol. The dark material appears to be concentrated on Iapetus' leading hemisphere, the side that faces forward as it orbits Saturn. Scientists believe this dark material comes from the Phoebe ring. As Iapetus orbits through the ring material, particles slowly accumulate on its leading face like bugs hitting a windshield, darkening that hemisphere over millions of years while the trailing hemisphere remains pristine white ice. Iapetus has another peculiarity, a massive ridge running almost exactly along its equator, stretching about 800 miles long, 12 miles wide, and rising up to 12 miles high in some places. This equatorial ridge makes Iapetus look like a walnut, with a seam running around its middle. Scientists aren't certain how this ridge formed. Perhaps Iapetus once spun much faster and the ridge is a frozen remnant of that ancient bulge, or perhaps it's the remains of a ring system that collapsed onto the moon's surface, or it might be volcanic in origin. Iapetus keeps its secrets, presenting its two-tone face and its mysterious ridge to the cosmos without explanation. Saturn's moon Hyperion is another oddball. It's irregularly shaped, about 225 miles across at its longest dimension, and it tumbles chaotically rather than keeping one face towards Saturn like most moons. Hyperion's rotation is unpredictable, tumbling in a way that makes it impossible to say which direction it will be facing even a few orbits in the future. Its surface is covered with sharp-edged craters that make it look like a sponge, giving it a texture unlike any other object we've observed. Each crater seems to have steep walls and a flat floor, as if something about Hyperion's composition prevents normal crater shapes from forming. Let your mind rest with these unusual moons now, Triton spiraling slowly toward its eventual destruction, Phoebe shedding dust to create an invisible ring, Iapetus wearing its coat of darkness on one side while the other gleams white, Hyperion tumbling unpredictably through space, each one a reminder that the solar system is full of exceptions, of worlds that refuse to follow the rules. Let us contemplate now the concept of gravity across different worlds, for the force that keeps us anchored to Earth varies dramatically throughout our solar system. We've mentioned that on Mars, you would weigh only 38% of your Earth weight, and on Jupiter, if you could somehow stand on a solid surface, you would weigh about 2.5 times your Earth weight, Jupiter's immense mass creating a gravitational pull that would make every movement exhausting, every step heavy with effort. But consider the smallest worlds. On Pluto, you would weigh only about 6% of your Earth weight. A person weighing 150 pounds on Earth would weigh just 9 pounds on Pluto, less than a newborn baby. You could jump extraordinary heights, perhaps 30 or 40 feet straight up with a good leap, hanging in the air for long seconds before slowly drifting back down to the icy surface. The escape velocity on Pluto, the speed needed to break free of its gravity entirely, is only about 2,700 miles per hour, compared to Earth's 25,000 miles per hour. On Pluto, leaving the world behind would require far less energy. On even smaller bodies, gravity becomes almost negligible. The asteroid Bennu, which NASA's OSIRIS-Rx spacecraft visited and sampled in 2020, is only about 1,600 feet across, roughly the height of the Empire State Building. On Bennu, you would weigh about 100,000th of your Earth weight. A 150-pound person would weigh about 1/40th of an ounce, less than a single M&M candy. If you tried to walk on Bennu, the slightest step would send you floating off into space. You couldn't walk at all in any normal sense. Even throwing a baseball at normal speed would be enough to send it into orbit around the asteroid, or escape into space entirely. The surface of Bennu turned out to be much more rugged than scientists expected. Instead of a smooth, sandy beach perfect for collecting samples, OSIRIS-Rx found a landscape of boulders and rocks. When the spacecraft touched down to collect its sample, its sampling arm sank more than a foot into the surface, discovering that beneath the rocky exterior, Bennu's material is loosely packed, almost fluffy, more like a ball pit than solid rock. This suggests many asteroids are rubble piles, collections of rocks and dust held together by their own weak gravity, with lots of empty space between the pieces. Saturn's moon Mimas, which we've mentioned as the source of the Cassini division through gravitational resonance, has a gravity about 1.5% that of Earth's. But Mimas is famous for another reason: it looks remarkably like the Death Star from Star Wars. Mimas has an enormous crater called Herschel crater, about 80 miles across on a moon only 246 miles in diameter. This crater is so large relative to Mimas that the impact which created it nearly shattered the moon entirely. On the opposite side of Mimas from Herschel crater, there are fractures and disrupted terrain, evidence that shock waves from the impact traveled through the moon and nearly broke it apart. Mimas survived, but just barely, left with a scar that gives it an uncanny resemblance to a fictional space station. Consider now Earth's gravity and how perfectly suited it is for life as we know it. Strong enough to hold onto a thick atmosphere, preventing it from escaping into space like Mars's atmosphere did. Strong enough to keep water liquid on our surface rather than boiling away into space. But not so strong that it crushes life into flatness, not so strong that it makes movement impossible or evolution toward complexity difficult. Our gravity allows birds to fly, allows trees to grow tall, allows us to jump and run and dance. It's one of countless factors that makes Earth a hospitable home, a balance point between the crushing weight of giant worlds and the ephemeral lightness of small ones. Picture yourself now experiencing these different gravities, leaping high on Pluto's icy surface, floating almost weightlessly around asteroid Bennu, struggling against Jupiter's heavy pull, feeling Earth's familiar embrace that allows you to stand and walk and live, each world offering a different relationship with the fundamental force that shapes the universe. As we approach the completion of our first journey through the solar system, let us reflect on the concept of distance and the vast emptiness that separates these worlds we've visited. Space, despite its name, is almost incomprehensibly spacious. If you could shrink the solar system so that the sun was the size of a basketball, Earth would be a tiny bead about 85 feet away, Mars would be about 130 feet distant, and Jupiter would be a marble nearly 450 feet from the basketball sun. Neptune, at this scale, would be almost half a mile away, a small marble so distant you could barely see it. And yet, despite these distances, the solar system is held together by gravity, that invisible force that reaches across millions and billions of miles, keeping planets in their orbits, moons circling planets, the entire family bound together in an intricate gravitational dance. The Sun contains 99.86% of all the mass in the solar system. Jupiter, despite being so large, accounts for most of the remaining fraction, and everything else, all the other planets, moons, asteroids, comets, and dust, makes up less than 0.1%. The Sun's gravity dominates everything, reaches out to the distant Oort cloud billions of miles away, defining the boundary of our cosmic neighborhood. Consider the journey of light across these distances. We know light takes over 8 minutes to travel from the Sun to Earth, but let's trace light's journey from the Sun outward through the entire solar system. It reaches Mercury in about 3.2 minutes, Venus in about 6 minutes, Earth in 8.3 minutes, and Mars in roughly 12.7 minutes. By the time light reaches Jupiter, about 43 minutes have passed. Saturn receives sunlight that left the Sun about 80 minutes earlier. Uranus receives light that's been traveling for about 2.7 hours, and Neptune, as we mentioned, receives light over 4 hours old. If an astronomer on Neptune looked at the Sun through a telescope, they would be seeing the Sun as it appeared 4 hours ago. If the Sun suddenly vanished, an impossible scenario, But imagine, Neptune wouldn't know for 4 hours. Earth would continue orbiting a sun that no longer existed for 8 minutes before we'd see it disappear. Pluto would remain unaware for over 5.5 hours. This is the nature of the cosmic speed limit. Even light, the fastest thing in the universe, takes time to cross the vast distances between worlds. The Voyager 1 spacecraft, launched in 1977, has been traveling outward through the solar system for nearly 50 years. It flew past Jupiter in 1979 and Saturn in 1980, then continued into the outer solar system. In 2012, Voyager 1 crossed the heliopause, the boundary where the Sun's influence gives way to interstellar space, becoming the first human-made object to leave the solar system. Yet despite traveling at about 38,000 miles per hour for nearly half a century, Voyager 1 is only about 15 billion miles from Earth, or roughly 161 times Earth's distance from Sunday. At its current speed, Voyager 1 would take about 40,000 years to travel the distance to the nearest star, Proxima Centauri, if it were headed in that direction, which it isn't. Voyager 1 carries a golden record, a phonograph record containing sounds and images from Earth, a message in a bottle cast into the cosmic ocean. The record includes greetings in 55 languages, sounds of Earth like ocean waves, wind, thunder, and birds, music from different cultures and eras, and images showing mathematics, the solar system, DNA structure, human anatomy, and scenes of life on Earth. The record is encased in a protective aluminum jacket with instructions for playing it, just in case, billions of years from now, someone finds it drifting through the galaxy. It's humanity's way of saying we were here, we existed, we reached out across the darkness to touch the stars. And here's something beautiful to end our journey. Right now, as you rest here, all the planets are out there, following their orbits, spinning on their axes, continuing the dance they've performed for billions of years. Jupiter's great red spot is swirling, Saturn's rings are catching sunlight, Mars's dust devils are spiraling across ancient plains, Enceladus is spraying ice into space, Neptune's winds are racing at supersonic speeds, and on countless moons and worlds, processes we've barely begun to understand continue in the darkness. The solar system doesn't sleep, it moves, changes, evolves, a living system of rock and ice and gas and plasma, all bound together by gravity and time. Let yourself rest now, knowing that you are part of this cosmic dance, made of atoms forged in stars, standing on a world that orbits a medium-sized star in a quiet corner of the galaxy, connected to everything we've visited tonight through the laws of physics and the shared story of our solar system's birth 4.6 billion years ago. Sweet dreams, traveler. The planets will still be there tomorrow, waiting patiently for you to return. Though our journey seemed complete, let us drift a little longer among the celestial wonders, for there are still quiet stories to tell. Return with me to Venus, that cloud-shrouded world, and consider what lies beneath those sulfuric acid clouds. The surface of Venus is perpetually dim. The thick atmosphere blocks so much sunlight that standing on Venus would feel like standing on Earth under a heavily overcast sky just after sunset. The light is there, filtering through miles of atmosphere, but it's diffuse and orange-tinted, creating a twilight world where shadows are soft and everything glows with a faint amber radiance. The atmospheric pressure on Venus creates another strange effect. The air is so dense that it refracts light in peculiar ways. If you could look toward the horizon on Venus, the dense atmosphere would bend light around the curve of the planet, allowing you to see farther than should be geometrically possible, as if the horizon extends beyond where it should. You might even see mountains and features that are actually behind the horizon from your perspective, their light bent by the thick atmosphere like light bending through a lens. Venus rotates so slowly that the winds in its upper atmosphere actually move faster than the planet's surface rotates, a phenomenon called superrotation. The clouds circle Venus every 4 to 5 Earth days, while the surface takes 243 days to complete one rotation. These winds reach speeds of about 225 miles per hour at the cloud tops, creating a perpetual hurricane that encircles the entire planet. Scientists still don't fully understand what drives this superrotation, what force pushes the atmosphere to race around the planet 60 times faster than the ground below turns. Let us visit Mars again and explore something we haven't yet touched upon, its two small moons, Phobos and Deimos. These moons are tiny, irregularly shaped, and heavily cratered. Phobos, the larger of the two, is only about 14 miles across at its widest point, while Deimos is even smaller at just 7.5 miles across. Both moons are so small that their gravity is insufficient to pull them into spherical shapes. They look like lumpy potatoes tumbling through space, captured asteroids that Mars claimed long ago. Phobos orbits Mars at a distance of only about 5,800 miles from the planet's surface, closer than any other moon orbits its planet in the solar system. It orbits so close and moves so fast that it completes 3 orbits around Mars every single Martian day. If you stood on Mars and watched Phobos, you would see it rise in the west, race across the sky in just 4 hours, and set in the east, opposite to how our moon moves across Earth's sky. And like Triton orbiting Neptune, Phobos is slowly spiraling inward toward Mars. In about 50 million years, Phobos will either crash into Mars's surface or, more likely, be torn apart by tidal forces, creating a temporary ring system around the red planet. Deimos, farther out, orbits Mars just above the distance where a moon would be tidally locked, taking about 30 hours to orbit. From Mars's surface, Deimos would appear as a very bright star rather than a moon. It's so small and distant that you couldn't see it as a disk with the naked eye. Deimos is slowly drifting away from Mars, the opposite of Phobos's fate, gaining altitude bit by bit over millions of years, eventually perhaps escaping Mars's gravity entirely and becoming an independent asteroid once again. The origin of Phobos and Deimos remains mysterious. They might be captured asteroids, as their composition suggests, but their orbits are surprisingly circular and aligned with Mars's equator, unusual for captured objects, which typically have more elliptical and tilted orbits. Perhaps they formed from debris when a larger object impacted Mars, or perhaps they're fragments of a larger moon that broke apart. Each possibility tells a different story about Mars's past, a puzzle written in the orbits of 2 small, dark moons. Settle deeper now into rest, breathing slowly, imagining the amber twilight of Venus's surface, the superrotating winds racing through its clouds, tiny Phobos racing across Mars's sky 3 times each day while Deimos hangs like a bright star, slowly drifting toward freedom. Each world layered with details, rich with stories we're only beginning to read. Let us drift now to Jupiter's moon Ganymede, which we mentioned briefly as the largest moon in the solar system, but there is so much more to discover about this frozen world. Ganymede is not only larger than Mercury, it's the only moon in our entire solar system known to have its own magnetic field. This magnetic field, generated deep within Ganymede's metallic core, creates a miniature magnetosphere around the moon, nested within Jupiter's much larger magnetic field like a bubble within a bubble. This makes Ganymede unique among moons, possessing a quality we usually associate only with planets. Ganymede's surface tells a story written in ice and rock, divided into two distinct terrain types. About 1/3 of the surface is dark, heavily cratered ancient terrain, perhaps 4 billion years old, scarred by impacts from the early solar system when debris was still settling into stable orbits. The remaining 2/3 is brighter, grooved terrain, long parallel ridges and valleys stretching across hundreds of miles, created by tectonic processes that reshaped the surface perhaps 1 to 2 billion years ago. This grooved terrain suggests Ganymede was geologically active relatively recently, its icy crust cracking and shifting, creating patterns that look almost like fingerprints when viewed from space. Beneath Ganymede's icy surface, scientists believe there's an ocean of liquid water, sandwiched between layers of ice at different pressures and temperatures. This ocean might be about 60 miles deep, lying beneath a crust of ice perhaps 95 miles thick. What's fascinating is that this ocean is likely salter than Earth's oceans, and the pressure at its bottom is so high that water ice forms again, but not the normal ice we know. At these extreme pressures, water forms exotic ice types called Ice V and Ice 6, which are denser than liquid water and sink to the bottom. Ganymede might have a layer cake structure, ice crust on top, liquid ocean, then another layer of exotic high-pressure ice, then another ocean, then more exotic ice, multiple ocean layers stacked like the levels of a building. Let's visit Saturn's moon Titan again and explore what we haven't yet mentioned, Titan's lakes and seas. We know they're made of liquid methane and ethane rather than water, but consider the landscape more deeply. Titan has hundreds of small lakes, mostly in its polar regions, and 3 major seas, Kraken Mare, Ligeia Mare, and Punga Mare. Kraken Mare is the largest, about 154,000 square miles in surface area, larger than the Caspian Sea on Earth, making it the largest known body of liquid on any world besides Earth. These seas are incredibly smooth. Measurements suggest the waves on Titan's seas are tiny, perhaps only a few millimeters high under normal conditions. This is partly because Titan's thick atmosphere and low gravity create different fluid dynamics than on Earth, and partly because the liquid methane and ethane are less dense than water. If you could sail a boat on Kraken Mare, it would be an eerily calm experience, gliding across an almost glass-smooth surface under hazy orange skies, with barely a ripple disturbing the liquid methane around you. The shorelines show features that suggest seasonal changes, liquid levels that rise and fall, perhaps analogous to monsoons, as methane evaporates and rains down in different regions across Titan's 29.5 Earth-year orbit around the Sun. Titan experiences weather, clouds form in its atmosphere, methane rain falls from the sky, and there's evidence of flash floods carving channels across the landscape. But this rain doesn't fall often. Scientists estimate it might rain on any given spot on Titan perhaps once every few decades or centuries. When it does rain, however, it can be intense. Models suggest Titan might experience violent storms that dump several inches of liquid methane in just hours, creating flash floods that rush through river channels and collect in lakes, gradually evaporating back into the atmosphere over years or decades, waiting for the next rare storm. The Huygens probe, which landed on Titan in 2005, sent back images from the surface showing a landscape of rounded pebbles made of water ice. Water is as hard as rock at Titan's frigid temperatures of -290 degrees Fahrenheit. the sky above the landing site appeared orange, and the sun was completely hidden by the thick haze, creating a diffuse glow rather than a distinct bright disk. For the 90 minutes that Huygens survived on Titan's surface before its batteries died, it showed us a world that feels both familiar and utterly alien, a place with weather, rivers, lakes, and seas, but rendered in methane instead of water, under skies that hide the sun, on ground made of ice as hard as granite. Close your eyes and picture Titan now, the smooth methane seas barely rippling in the gentle breeze, orange haze filtering the distant sunlight, rare rain falling from thick clouds, ice pebbles lying on the shore where liquid methane laps gently at the beach, a world that mirrors Earth in structure but transforms everything through the alchemy of cold and distance. Let us drift back to Mercury once more and contemplate a phenomenon that occurs only on this closest planet to the Sun, something astronomers call the double sunrise. Because of Mercury's peculiar combination of orbital and rotational speeds, there are locations on Mercury's surface where, if you watched carefully, you would see the sun rise partway above the horizon, then stop, reverse direction and set again briefly, then rise once more and continue across the sky. This happens because Mercury's orbital speed varies as it travels along its elliptical path, moving faster when closer to the Sun and slower when farther away, and at certain points, this varying orbital speed temporarily overtakes its rotation speed, making the Sun appear to move backward briefly. Similarly, at some locations on Mercury, the Sun appears to pause at its highest point in the sky, noon, hovering there for several Earth days before slowly beginning to descend. Time stretches and contracts on Mercury in ways that challenge our Earth-based intuitions about how days should work. These double sunrises and lingering noons create what astronomers call hot poles, specific longitudes on Mercury's equator that, through these timing peculiarities, end up facing the Sun for extended periods when Mercury is at its closest approach, making these spots the hottest places on an already scorching world. Journey with me now to the outer solar system, beyond Neptune, to explore the Kuiper Belt more deeply. We mentioned this region earlier, but consider its population. Scientists estimate there may be over 100,000 objects larger than 60 miles across in the Kuiper Belt, and countless smaller ones. These are pristine remnants from the solar system's formation, preserved in a deep freeze for 4.6 billion years. They're composed of mixtures of rock, metals, and frozen volatiles like water, methane, and ammonia, materials that never coalesced into planets but remain scattered across this distant region, like pieces of a puzzle that was never completed. Among the Kuiper Belt objects is Arrokoth, which became the most distant object ever visited by a spacecraft when New Horizons flew past it on January 1, 2019. Arrokoth has a bizarre shape. It looks like two spheres gently touching each other, creating a contact binary that resembles a cosmic snowman. Arrokoth is about 22 miles long overall, colored a reddish-brown by organic molecules called tholins that form when sunlight hits methane ice. The contact binary shape tells scientists that Arrokoth formed gently, with two separate objects drifting together at walking speed and sticking, rather than smashing together violently. It's a relic of gentle formation processes, preserved in the outer solar system where nothing has disturbed it for billions of years. The Kuiper Belt isn't uniform, it's structured into different populations and resonances, shaped by Neptune's gravity over millions of years. Some objects orbit in a 2:3 resonance with Neptune, completing exactly 2 orbits for every 3 Neptune orbits. These objects are called Plutinos because Pluto is among them, and there are thousands of known Plutinos sharing this orbital pattern. Other Kuiper belt objects have been scattered into more distant, eccentric orbits by gravitational encounters with Neptune. Some of these scattered disk objects venture out to hundreds of astronomical units from the Sun before falling back inward. There's evidence suggesting an even more distant population called the detached objects, bodies whose orbits never bring them close enough to Neptune to be influenced by its gravity, yet their orbits are still mysteriously aligned in ways that suggest something massive is affecting them. This has led to speculation about a possible Planet 9, a hypothetical world perhaps 5 to 10 times Earth's mass orbiting in the distant outer solar system, hundreds of times farther from the Sun than Earth is. If it exists, Planet 9 would take 10,000 to 20,000 years to complete one orbit. Searches are ongoing, using powerful telescopes to scan the sky methodically, looking for the faint moving that would signal another major planet in our solar system. Whether Planet 9 exists or not, the outer solar system clearly holds mysteries we haven't yet solved. The Kuiper belt blends gradually into the scattered disk, which blends into the inner Oort cloud, which extends into the outer Oort cloud, layers upon layers of icy bodies, perhaps trillions of comets waiting in the darkness, forming a spherical shell around our entire solar system extending halfway to the nearest star. This is where comets sleep, where they wait for the gentle gravitational nudge from a passing star or the tidal forces from the galaxy itself to send them falling inward toward the Sun. Rest now with thoughts of these distant realms, Mercury's double sunrises and lingering noons, the Kuiper belt's 100,000 frozen worlds, Arikatha's gentle joining preserved for 4.6 billion years, mysterious alignments suggesting unseen planets, trillions of comets sleeping in the Oort cloud's embrace. The solar system extends farther than we can easily imagine, fading gradually into the space between stars. As our journey draws to its gentle close, let us contemplate one final marvel, the pale blue dot that is our home. In 1990, at the request of astronomer Carl Sagan, the Voyager 1 spacecraft turned its camera back toward the inner solar system from a distance of 3.7 billion miles and took a photograph of Earth. In that image, our entire world appears as a tiny speck, less than a single pixel, suspended in a beam of scattered sunlight. That pale blue dot contains everyone you've ever known, every human who has ever lived, every civilization, every triumph and tragedy in our species' history, all of it happening on that tiny mote of dust suspended in a sunbeam. From that distance, you couldn't see continents or oceans, couldn't distinguish countries or cities. Earth's brightness in that image came partly from sunlight reflecting off our oceans and clouds, the same water that makes our world uniquely hospitable to life. Earth is the only planet in our solar system where water exists in all three states simultaneously and abundantly, ice at the poles and mountaintops, liquid water covering most of our surface, and water vapor perpetually cycling through our atmosphere. This hydrological cycle, driven by the Sun's warmth and Earth's perfect distance from it, is one of the fundamental processes that makes our world alive. Earth orbits the Sun in what astronomers call the habitable zone or Goldilocks zone, the region around a star where conditions are neither too hot nor too cold for liquid water to exist on a planet's surface. Venus is too close, baking under greenhouse heat. Mars is too far, with most of its water frozen or lost to space. But Earth sits in the sweet spot, about 93 million miles from the Sun, where temperatures allow water to remain liquid, where the air pressure is just right, where life can flourish in astonishing diversity. Our atmosphere is precious beyond measure, a thin shell only about 60 miles thick, though most of the air we breathe exists in the lowest 6 miles. If Earth were the size of an apple, our atmosphere would be thinner than the apple's skin. Yet this thin envelope protects us from harmful radiation, burns up meteors before they reach the surface, distributes heat around the planet, and contains the oxygen we breathe, oxygen produced by billions of years of photosynthesis by plants and algae, transforming Earth's atmosphere from one that would be toxic to us into one that sustains us. We breathe the exhalations of forests and oceans, connected to all life through every breath. Earth is geologically active, with plate tectonics constantly reshaping our surface. This activity is crucial for life. It recycles carbon through the carbon cycle, regulates our climate over geological time, and creates diverse environments from mountain peaks to ocean trenches. Our planet's magnetic field, generated by our liquid iron core, shields us from solar wind that would otherwise strip away our atmosphere as happened to Mars. The Moon stabilizes our tilt, giving us regular seasons. Jupiter's gravity protects us from excessive bombardment. We exist in a web of cosmic circumstances, each element necessary for our continuation. And consider this, in our entire solar system, among all the planets, moons, asteroids, and comets, Earth is the only world we know with certainty harbors life. We may discover microbial life elsewhere, perhaps in Europa's ocean, or Enceladus's warm vents, or ancient Mars, or beneath Titan's methane seas, but for now, Earth stands alone as the only world in the cosmos confirmed to be alive. Every form of life we know, from bacteria to blue whales, from mosses to giant sequoias, from the simplest viruses to the complexity of human consciousness, exists here and only here as far as we can confirm. This makes Earth not just our home, but a sanctuary, a rare and precious jewel spinning through the vast darkness. As you drift towards sleep, hold this thought: you are resting on a living world, orbiting a stable star, in a solar system filled with wonders we're only beginning to understand. Above you, the planets continue their ancient dance, Mercury racing close to the Sun, Venus shrouded in clouds, Mars dreaming of its watery past, Jupiter swirling with eternal storms, Saturn wearing its crown of rings, Uranus rolling sideways through space, Neptune swept by supersonic winds, and Pluto with its heart-shaped glacier, far out in the cold darkness. All of them are there, all of them waiting. And you are connected to all of them through gravity, through the shared materials from which we're all made, through the story of our solar system's birth in a cloud of gas and dust 4.6 billion years ago. Sleep now, traveler, and dream of worlds where methane rain falls on orange shores, where ice geysers spray into rings, where volcanoes build mountains 3 times higher than Everest, where magnetic fields wobble and winds race faster than sound, where moons spiral slowly toward their doom and others drift toward freedom, where double sunrises paint the sky and footprints wait in airless dust for millions of years. The universe is vast and strange and beautiful, and you are part of it, made of stardust, resting on a pale blue dot, beneath a sky that opens onto infinite wonder. Good night. Sweet dreams. The planets will be waiting when you wake.